All right, today we are diving into one of the most beautiful and frankly surprising ideas in all of modern math, random matrix theory. We're going to see how some of the most profound, predictable order can pop up out of pure absolute chaos. Let's get right into it.
So it all kicks off with a really simple question. Just imagine a big grid, like a spreadsheet. What do you think happens if you fill every single one of those cells with a number that you've picked completely at random? I mean, you'd probably expect just a total mess, right? A meaningless jumble of digits.
And on the surface, you'd be totally right. What you've just made is called a random matrix. It's a mathematical thing built on nothing but pure chance. But trust me, that is just scratching the surface of our story.
Okay, so to be super clear, a random matrix is exactly what it sounds like. It's a grid, a matrix, where every single entry is a random variable. The whole thing is built on chance. It's like a snapshot of randomness. Because, and this is the amazing part, hidden deep inside all of that apparent randomness, there's a secret. There's this unbelievable amount of structure and order. And to find it, we have to look at something that's kind of like the matrix's hidden DNA.
So, what is this hidden DNA I'm talking about? Well, that brings us to the first part of our mystery, eigenvalues. See, to really get what a matrix is all about, you have to understand these special numbers.
Now, hey, don't worry about this super complex math here. For our purposes, just think of eigenvalues as these fundamental properties of the matrix. They're like its unique fingerprint or its genetic code. They tell you the really important stuff about it.
So, it seems totally logical, doesn't it? If the matrix is just a big box of random numbers, then its eigenvalues, its DNA, should also be completely random. They should be scattered all over the place with no rhyme or reason, right? Well, this is where things start to get really weird. And this is the part that just doesn't make sense at first. If you just throw a bunch of random numbers on a line, they'll clump up. Actually, the most likely distance between any two of them is 0. They can land right on top of each other. But the eigenvalues of a random matrix, they do something totally different. They actively avoid each other. It's almost like they can feel each other's presence and they need their personal space. The chance of finding two right next to each other is literally 0. We can actually see this strange repulsion in this curve, which is called Wigner's surmise. Just look at the graph. The probability of finding two eigenvalues with 0 spacing is, well, it's 0. The curve starts at the bottom, goes up, and then falls away. The bottom line here? This isn't random clustering at all. This is definite, predictable structure. Probably the best way to picture this comes from the physicist Eugene Wigner himself. He said it's like birds on a wire. They don't all clump together in one spot, but they're not perfectly spaced out either. They just naturally keep a certain distance from each other. Not too close, not too far. That's eigenvalue repulsion in a nutshell. But this whole repulsion thing is just the first clue. The mystery gets so much deeper when we zoom out and see how this one little behavior creates an even bigger and, frankly, more unbelievable pattern. So what if we really scale this up? Instead of just one random matrix, let's imagine we generate thousands of them, each one huge. And then we collect every single eigenvalue from every single one of those matrices and just throw them all onto one big graph. What kind of shape would that giant cloud of millions of numbers make? The result is, it's absolutely mind-blowing. When you plot the density of those millions upon millions of eigenvalues, what emerges from the chaos is a perfect, predictable shape, a semicircle. This isn't some fluke. It's a universal law for large random matrices, and it's known as Wigner's semicircle law. It is pure order born from pure randomness. So how is that even possible? How does such a perfect, beautiful shape just emerge from chaos? Well, the key is to stop thinking about the math for a second and start thinking about the physics, using this really elegant idea called the Coulomb gas analogy. The secret to unlocking this whole mystery is really about changing our perspective. We have to stop thinking of these eigenvalues as just, abstract numbers on a line. And instead, start imagining them as actual physical things, like tiny particles that all have the same electric charge, and they're all floating around in some kind of fluid, stuck moving along a single line. So this analogy works because you've got two forces fighting each other. First, you've got confinement.
Imagine an invisible force, kind of like the shape of a bowl, that's pulling all of our little particle eigenvalues toward the center so they can't just fly away. But second, at the same time, you've got repulsion. Just like we saw before, all those particles are pushing each other apart. So what's the end result? Well, you get equilibrium. That perfect semicircle shape is the stable, lowest energy arrangement where those two competing forces find their perfect balance.
Okay, so you might be thinking, this is a really cool mathematical party trick, but does any of this actually matter in the real world? And the answer to that is a huge resounding yes. See, this whole principle of order just emerging out of chaos, it's not just a cute little math curiosity. It turns out to be a fundamental feature of so many complex systems that we see all around us in the universe. And the applications are they're everywhere and in the most unexpected places. In physics, it helps us model the energy levels inside the nucleus of a heavy atom, a system so ridiculously complex that we might as well treat it as random. It's used to describe the behavior of complex quantum states. In finance, it helps analysts filter out the random noise from the real signals in chaotic market data. It even helps engineers understand how waves scatter when they move through disordered materials. And this leads us to this really powerful, almost backwards-sounding idea. Sometimes a system is just so complicated, so messy, that the best way to understand it is to stop trying to track every little detail and just assume the whole thing is random. By swapping that messy reality for an idealized random matrix, we can use these predictable laws of randomness to uncover deep, fundamental truths about the original system. Which leaves us with one final fascinating question to think about. If a structure as perfect and predictable as a semicircle can just spontaneously bubble up out of pure, unguided randomness, it really makes you wonder. In all the other chaotic, complex systems in our world, from economies to ecosystems to the weather, where else might we be missing the pattern that's hidden in plain sight?